Hello everyone and welcome to OneClass. My name is Jeff Krause. I have a PhD in physical chemistry and today I'm going to run through a few undergraduate level physics questions. So here's our first one. I'll just read it off. So we have a wire that's 1.60 meters in length. And it carries a current of 32.3 milliamps. And the whole wire can be arranged as a single loop in a circle shape, a square shape, or an equilateral triangle. And we can make the whole thing into a compact coil with end turns. We're asked to calculate the magnetic moments in each case. So the magnetic moment is defined as through the torque which is exerted in the presence of an external magnetic field, where the mu vector I show here is the magnetic moment. And so the way you can define the magnetic moment is by basically expanding what you would expect the torque to be and getting it into this form, and then what comes out is the magnetic moment. Now for symmetric shapes like this, our magnetic moment is going to come out to be IA. In this case, actually, IA, and then we would use the right-hand rule to define the magnetic moment. And so I'm just going to call it K hat, where if I have, say, a circle with current running clockwise, let's actually go with current running counterclockwise. So my fingers would curl around, then my magnetic moment would go out, straight up. Right, so fingers curl around. And so then my thumb would point in the direction of the magnetic moment. Quite scary looking hand, but I think that's kind of explanation. And I'm just gonna erase that because it kind of scares me. All right, but our magnitude of our magnetic moment, which I'm just going to call mu from now on, is just IA. Okay, so for a single turn circle, then our length is 1.60 meters. The length of a circle is its circumference, so 2 pi r is equal to 1.60 meters. So then r is equal to 1.60 over 2 pi. And so then its area is pi r squared, which is equal to pi times 1.60 meters over 2 pi squared. Which, if we do it all out, comes to be 0.204 meters squared. So then its magnetic moment for a wire which carries 32 times 10 to the minus 3 amps times this area is 6.58 times 10 to the minus 3 amp meters squared. So that's our that's for our circle. And then for our square, our square is going to be, each side will be length L. And so our circumference is going to be 4L, which is equal to our total length, which is in this case 1.60 meters. So L is 1.60 over 4. And so our area is L squared for a square, which is 1.60 meters over 4 squared, which is 0.16 meters squared. And so then our magnetic moment is 32 times 10 to the minus 3 amps times our area, which comes out to be 3.986 times 10 to the minus 3 amp meters squared. So that's for a square. And then for equilateral triangle, oops, oh, that was a mistake there. So our equilateral triangle is going to have each side of length L, and our area is going to be 1/2 the base times the height, or the height times the base, as I've written it in here. And so it's an equilateral triangle, meaning each of these are 60 degrees. So our height here is, I guess I might as well do it this way. So then the sine of 60 degrees is our height over our length, or our height is sine 60 times our length, which is root 3 over 2 times our length. And just to make that slightly more clear, it's square root of 3 over 2 times our length. So our area is root 3 over 4 L squared, which is root 3 over 4 times our, so our length, and now for our circumference here, so our 3 times our L is the 1.60 meters, so L is 1.60 meters over 3. So then this is 1.60 meters over 3 squared. And if we do that all out, it comes to 0.1234 meters squared. And so then our magnetic moment is 32 times, I dropped it here, sorry, 32.3 times 10 to the minus 3 amps times our area, which comes to be 3. Oh, alright. Okay, gotta be slightly more careful with how I write here, sorry. So this here actually comes to 5.168, sorry, 5.168 times 10 to the minus 3 meters squared. And this one here actually comes to the 3.986. Sorry about that. There we go. All right. And then for a circular loop with n turns, so we have a circle, put that with multiple turns. Our area is still going to be pi r squared, but n times our length, or sorry, but our length now is the 1.60 meters, which is going to be n, so our number of turns times 2 pi r, where r is our radius for our circle, n is our number of turns, and so we have n of our circumferences. So then r is 1.60 meters over n 2 pi. So then our area is pi r squared, so 1.60 over n 2 pi squared. And so then our moment is our current, 32.3 times 10 to the minus 3 amps times our area, which comes out to be 0.204 meters squared over n squared. And so then it's pretty much it's the same as the circle. Amp meter squared, but over n squared. There. Okay. So then, I'll just circle that one. So there's for our coil, it then turns. All right, so then if we scroll up here and just check the solution with what was given. All right, so when the wire is a circular loop, we get an area of 0.203, 204, so that's just rounding differences. Our magnetic moment looks to me like they're missing a 10 to the minus 3, but that's okay. That's for n turns, so they just skipped ahead. They're also missing the n squared. So this one actually has, for the square loop, it looks like they made the same mistake as I did by jumping ahead. So where's their area? Well, squared over 16, 1.6. So if they actually did the calculation shown there, that would be off, because this is the magnetic moment I believe I get. So I think they're just wrong there. And The equilateral triangle looks right. I might just double check their math though with the second one just to be sure. So 32.3 times 10 to the minus 3 times 0.16 is the 5.168. And then if I do theirs, yeah, so that's where, so they missed the L squared in this for the square. Okay, so I'm just going to say for A, they missed 1 times 10 to the minus 3. For B, missed L squared. Okay, and so it's basically just small mistakes, but I'm still going to just mark